Hi, Assalamualaikum warahmatullahi wabarakatuh. We are from Group Skittles. My name is Izzah Zulaikha binti Muhammad Fauzi. My matric number is 22165002. My other two members are Robiata Adawiyah binti Muhammad Alwi, 22178008, and Nur Aina Fitra binti Omar, 221504. So we are going to present about our system, which is IIUM Bus Tracker.
Okay, so for our project purpose, the purpose of our project, which is IIUM bus tracking system, is to enhance the overall transportation experience for students and staff by providing a reliable, efficient, and user-friendly platform to track campus bus location in real time. The system aims to address common challenges such as unpredictable bus arrival times, delays, and lack of effective communication about bus schedules.
Hi, my name is Rana Fitra binti Omar. My matric number is 221504. So I will present for the project scope of our project. So the objective of IIUM Bus Tracker project is to revolutionize the university's bus transportation system by introducing a real-time tracking and efficient management. So this system is designed to provide accurate, real-time bus location and schedule, along with timely notification for the student, driver, and administrator. By leveraging the GPS technology and integrating mapping service such as Google Maps, this system ensures a precise update that user can rely on for their future planning for transportation effectively. So our target outcome is to create a transportation ecosystem within IIUM communities that enhance the functionality, reduce stress for the student and IIUM staff, and foster seamless communication among all the stakeholders involved. Through this solution, we aim to transform the commuting experience into one that is convenient, reliable, stress-free, and ensure the operational efficiency while meeting the growing the needs of IIUM community. For the stakeholder for our project, which is IIUM bus tracker system, we do involve with a multiple stakeholder, which is we do have 4 student, admin, transportation unit at IIUM, and bus driver. So firstly, student, which is a primary user for the system that rely on the apps to view the real-time bus location and schedule. This allow them to plan their commutes effectively by checking estimate arrival time, ATA. Additionally, the student also can receive the timely notification about any delays, route changes, and important announcement, ensuring they are always informed and prepared. Next, for the admin are responsible for managing the system and access permissible with the system, which they have play a critical role in maintaining the accuracy and reliability. Admin also handle the maintenance, task, system audit, and troubleshooting to ensure the platform runs seamlessly for all users. Next, for the transportation unit at IUM, that also known as vehicle management department, can oversee the operational aspect of the bus system. They update the bus schedule, route within the system, and monitor the performance and location of the bus in the real-time user for the tracker. So their responsibilities include addressing system-related issue and ensure the overall efficiency of the transportation across the IUM campus. Lastly, for the bus driver. Bus driver is essential to the functionality of the system, which they operate the GPS-enabled device to share the accurate bus location in the platform. So they have to report any delays that might impact the schedule or coordinate closely to the transportation unit to add on for the operational challenges.
Moving on to the functional and quality requirement of this project, the first one is real-time GPS tracking, which the system must provide live tracking of bus movement on all campus routes using GPS data. The second one is bus route display, which a map-based interface to show the current location of buses on their respective routes. The third one is ETA, estimated arrival times, which the display predicted the arrival times of buses at various stops based on real-time data. Next one is push notifications, which GPS data accuracy within a 10-meter radius for reliable real-time tracking. Next is route schedules, which display the full bus schedules and allow users to compare actual bus location to schedule items. Schedule time. Next, route schedules, which we display the full bus schedules and allow users to compare actual bus location to scheduled times. The last one is admin dashboard, which will allow IM Transportation Office to monitor bus movement, driver performance, and system analytics.
Okay, now let's look at the non-functional or quality requirement that ensure our IIUM bus tracking system delivers a reliable and seamless experience for its user. So, the first one is performance. Our system prioritizes performance by ensuring that real-time information is updated with a maximum latency of just 5 seconds. This minimal delay is crucial for providing users with accurate and timely updates, which is a key requirement for a reliable tracking system. Second one is scalability. Scalability is another critical aspect. The system is designed to handle surge in user traffic, especially during peak periods such as class transitions or exam days. This ensures that even under heavy loads, the system remains efficient and responsive, meeting the needs of a growing user base. The third one is usability. We also emphasize usability. The system features a user-friendly and intuitive design, making it easy for students and staff to navigate on both mobile and desktop platforms. Accessibility is the top priority to ensure everyone can use the system without any hassle. Next is the accuracy. Accuracy is essential for real-time tracking. The system provides GPS data with a precision of up to a 10-meter radius, ensuring that users receive reliable and trustworthy location updates at all times. Next is the security. So to protect user data of the system implements robust security measures. These include authentication protocol and encryption, safeguarding sensitive information and ensuring user privacy. Unauthorized access is prevented, making the system safe for everyone. And the last one is the availability. Finally, availability is critical. The system guarantees an impressive uptime of 99.9%, ensuring uninterrupted access. Regular maintenance, schedules, and dedicated technical support are in place to promptly address any issues, keeping the system functional and reliable for users. Okay, so this is the use case diagram for IIUM bus tracker system. So basically, in our use case, we have three actors, which is student, admin, and IIUM vehicle management department, or for short, VMD. So we have six use case. Which for student we have three, which is select bus route, enable location service, track bus. And for admin, we have two use case, which is monitor system and update GPS data. And for VMD, we have manage bus information. Okay, so for the first use case, which is select bus route, the actor is the student. So basically, the student select their desired bus route from the available option. So the trigger is the student opens the system to view available bus routes. Preconditions is the student must be logged into the system. Post condition is the selected bus route is displayed on the interface. So basic flow is the first step is user log into the system, and the system authenticates the student and grant access. The second step is user selects a desired bus route from the displayed list, and the system display the available bus route. The third step is system confirms and display the selected route. The alternative flow, if no bus routes are available, the system displays a message indicating no active route. Okay, so for the second use case is enable location service. So the actor is student. Basically, the student enables location services to access real-time bus tracking features. The trigger is the student attempts to track a bus. The precondition, the student must have granted location access to the application. And the post condition is location services are active and the system can track nearby buses relative to the student. So for the basic flow, first step is user respond to the system prompt to enable location services and system prompt the user to enable location services. The second step is user grants location access if prompted by the device, and the system activates location service upon receiving permission. And the third step is system begins tracking the user's location. Alternative flow is if location services are not enabled, the system display an error message requesting permission. The third use case is track bus. The actor is student. So basically, the student tracks the real-time location of buses on their selected route. The trigger is the student select the track bus option. The precondition is location service must be enabled and the student must have selected a bus route. And the postcondition, the system display the real-time location of buses on the selected route. The basic flow is the first step. User select a bus route and the system retrieve the real-time GPS data for buses on the selected route. The second step, user taps the track bus option and the system display the current location of buses on the map interface. And the alternative flow, if GPS data is unavailable, the system displays a message indicating real-time tracking is delayed. Okay, move on to the next use case, which is manage bus information. The actor is IUM Vehicle Management Department, or VMD. So basically, VMD updates and manage bus schedule, route, and status within the system. The trigger is when VMD initiates a request to update bus schedule or routes. The precondition is VMD must have admin level access to the system. And the post condition, updated bus information is reflected in the system and accessible by student and staff. So for the basic flow, the first step is user logins to the system using admin credentials, and the system authenticates the admin and grant access to update features. The second step is user update the necessary information related to bus schedule or routes, and the system save the updated bus information in the system. And the third step is system reflect the changes in the interface accessible to all users. For alternative flow, if update fail, the system display an error message and logs the issue. Okay, so for the fifth use case, which is monitor system, the actor is admin. So basically, admin monitor the system to ensure smooth operation and detect potential issue. The trigger is when admin logs in to review system performance. Precondition is the admin must have system level access, and the post condition is the system is operating as intended and issues are addressed promptly. For the basic flow, the first step, user log into the system and the system display an overview of current bus operation and system performance. The second step is user review system reports and alerts, and the system highlights any detected issue or anomalies. The third step is user take corrective action if issues are detected, and the system log a corrective action performed by the admin. So for the alternative flow, if an issue is detected, the admin take corrective action based on the system alert. And for the last use case, which is update GPS data, the actor is admin. And the description, the admin ensures the GPS data for buses is up to date and accurate. The trigger is when admin initiates a request to update GPS data. So for the precondition, admin must have access to the GPS updating interface, and the post condition, GPS data is accurate and reflect the real-time location of buses. So for the basic flow, the first step is user log into the system. And system display the current GPS data for all buses. The second step is user identifies inaccurate or outdated GPS data and system save updated GPS data to the system. And the third step is user updates the GPS data as needed and system reflect the updated GPS data in the tracking feature. For the alternative flow, if GPS update fail, the system display an error message and logs the issue for further action.
So for the flowchart, the process begins with user opening the application, which will display the start screen and home page. And then users can select bus route that is available, and then checks whether GPS location services are enabled on user device. If GPS is not enabled, the application prompts user to activate and recheck the GPS status. Once the GPS enabled, the system will retrieve the real-time location of the bus using GPS data. And lastly, the application displays the current bus location on a map for user to track. So this ensures that users can monitor the bus and efficiently.
For the activity diagram, this activity diagram shows the interaction between the three entities, which is the student, IUM bus tracker, and the admin. So the process begins with the student initiate a request to track a bus by select the bus route. Then the system will validate the request and retrieve the relevant bus location data using the GPS tracking. If necessary, admin will ensure the system accuracy, performance maintenance to address any potential issue that may arise during the process. So when the data is retrieved and processed, the IUM bus tracker system will display the current location on the bus on the map interface for the student to review. So the interaction concludes successfully when the student receives the request bus location in real time. So this activity diagram emphasizes the seamless collaboration between the student, system, and admin, ensuring an efficient and user-friendly experience for the bus tracking within the IUM campus.
Okay, let's dive into the strategies we've implemented to ensure the IUM bus tracking system delivers on its quality expectation. We'll break this down into key areas. First, for performance, we are using MQTT, which is the message queuing telemetry transport, to enable efficient real-time data polling. This ensures that bus location updates are fast and reliable. Additionally, load balancing is in place to distribute traffic evenly, especially during peak hours, ensuring the system doesn't slow down. Next is the scalability. Scalability is a priority, so we've enabled horizontal scaling, meaning we can add servers as needed to accommodate more users. We've also applied database partitioning to handle large dataset effectively, ensuring the system remains responsive as it grows. Next is the accuracy. For data accuracy, we are using error correction algorithm to improve the precision of GPS data. We are also employing data fusion techniques and regularly calibrating GPS devices to maintain consistent accuracy. Next is the security. Security is critical. So we've implemented SSL or TLS encryption to protect data in transit, along with Open Authorization 2.0 for secure authentication. Additionally, we are using role-based access control and token-based API authentication to ensure only authorized users have the access. Next is the availability. So to ensure availability, we've deployed redundant servers and failover system to minimize downtime. Monitoring tools will proactively detect any issues, and automated backups are in place to support disaster recovery. And the last one is maintainability. So the system is designed with modularity, making updates and troubleshooting simpler. We've also ensured version control and provided detailed documentation to assist developers and administrators.
So this is the component diagram for the bus schedule and the estimated time arrival. So the GPS device provides live bus location data by connecting the bus tracking system. It serves as the primary source of real-time coordinates, enabling accurate tracking and updates for other components in the system. I will explain more on how we implemented it in the code for the prototype.
This is the class diagram for the user notification service, which is responsible for sending notification to user when buses are approaching or delayed. The design is based on the observer design pattern, ensuring efficient communication between components. At the core of this design are the subject and observer interfaces. The subject interface defines the method for registering, removing, and notifying observers. The observer interface ensures that any observer, like the user notification service, can receive updates via the update data method. The bus tracking service class implements the subject interface. It maintains a list of observers and track bus location. Whenever bus location data is updated through the update bus data method, it calls notify observer method to push updates to all registered observers. This class implements the observer interface and subscribe to updates from the bus tracking service. It uses a notification preferences map to store user preferences for notification channel. Based on these preferences, it sends notification through the relevant channels. There are two notification channels. The first one is push notification channel, and the second one is SMS channel, which define how messages are sent to users. Both implement methods for sending notification, ensuring flexibility in how users receive updates.
The main implementation of the subject interface is bus location service class. So this class manages the state of all buses, include their location and route. It uses maps to store all the location of each bus and another map to store the routes assigned to the bus. It's also meant a list of observer and provide method to register, remove and notify them. So the update bus location method updates a bus location and then trigger the notify observer method to inform all the observer of the changes. So finally, we have the main class that which bring everything together. It signalize the bus location service, create and instead of the map display observer, register as an observer, and then define the bus route for the two bus, simulate location, update for each of them. So as an update occur, observer is notified and prints the bus route and location to the console.
So now I'm going to present about the prototype for bus schedule and estimated time arrival. So the first is the subject, which is the bus location service. In this subject, it maintains a list of observers and notifies them when there is an update. So the method update bus location generates bus event and calls notify observers to update all registered observers. And then we have an observer, which is ETA calculator. It listens for updates from the bus location service just now and implements the updates method to handle the event. And lastly, the bus event. This class represents the event object containing bus ID, stop name, and the ETA. It is the data carrier for the updates. So this is the output of this prototype, which will show the ETA update, which include the bus ID, the bus number, and then which stop and what is the duration for the ETA, estimated time arrival.
Now let's go through the coding for user notification service step by step. Okay, we start with the subject and observer interfaces. The subject interface defines method to register, remove, and notify observers. The observer interface ensures that any observer has an update method to handle incoming data. Okay, next, the bus tracking service class. The bus tracking service implements the subject interface. It maintains a list of observer and notifies them whenever the bus location is updated. So here's how the update bus data method works. Okay, next, the user notification service class. The user notification service implements the observer interface. It receives updates and send notification based on user preferences. So here is the example of the update and send notification method. Okay, now move on to notification channel class. Finally, the push notification channel and SMS channel implement the notification channel interface. This channel define how notifications are sent. Okay, so for instance, like the below coding. Okay, so here is the main class that sets up the system. We register the user notification service as an observer, add user preferences, and update the bus data. Okay, so for the output, as you can see, both push notifications and SMS are sent to user 1, while only a push notification is sent to user 2. So to summarize, the user notification service ensures users receive timely updates about bus location and delays. The observer design pattern makes the system modular and easy to extend.